Now we're going to talk about moving currents. So we were talking about moving charges in magnetic fields. And what are moving charges if you get a whole bunch of moving charges? Current. So it makes sense that current is going to be affected by magnetic fields as well. And it turns out current is affected by magnetic fields and currents create magnetic fields. And we're going to learn more about that next week. So this picture is about the currents creating magnetic field, that if you brought a compass near a current carrying wire, it would deflect a compass needle. What we're going to talk about today is how a magnetic field can create a force on a current carrying wire. So it can push the electrons sideways, as we learned with our right-hand rule. If you've got a bunch of electrons flowing in a wire, it will physically push that wire sideways. So here's a lot of development, blah, 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 that's leading to a new equation. So if you want to read all the development, it's there. It's leading us to a new equation. This one dealt with a charge and the charge's velocity in a B field. This is dealing with current, the direction of current, and a B field. It's also a cross product. So this would be the magnetic force on a current carrying wire. Okay, so L, the magnitude of L, or L, is the length of the wire. And then the direction of L is the direction of current flow. So that's what L, vector L means. It's a little strange. Because it's a cross product, you can also write this as ILB sine phi. And now we're not going to be dealing with vector components because current in a wire, wires bend. It doesn't really make a lot of sense to do vector components with this one. Okay, example 27.7. What the heck is this one asking us? Okay, a straight horizontal copper rod carries a current of 50 amps from west to east. So there's a chunk of wire and the current is flowing to the east and the current equals 50 amps in a region between the poles of a large electromagnet. In this region there's a horizontal magnetic field towards the northeast. Show me with your hands what direction is northeast. Chris got it? Wrong. You got it, you got it, you're wrong. You got it, you got it, you got it. Oh boy. All right, north, south, east, west. If you ever get mixed up between east and west, which you shouldn't, you live on the west coast. The ocean is that way. Landlocked states have an excuse. You guys have no excuse.
It's really funny. I went across the country for a trip, and they're all like, "Oh, you live in Oregon. Oh, you live out in the West." And I was like, "Oh, I guess I do." They're like, "So
anything west of the Mississippi is the West."
So they're like, "So is everyone out there like? Is it still like cowboy towns?" I'm like, "Well,
This sounds just like every conversation I had when I moved to Ohio.
I'm like, "Well, I live in one, but no one else does." Like, so
no, I think the majority of the West is still rural.
It is.
But it's just funny, like they have this idea that like the West, if it's not LA, it's like
Wild Wild West.
Yeah.
Yes, cowboys and Indians.
Yeah.
Yes.
They're like, "So does everybody ride horses out there?"
Yeah.
Good Sundays.
We have cars. We have cars. Yeah, it's really funny.
Well, it goes both ways, because I had a lot of misconceptions about Ohio too. So actually a lot of them were right, but I'm allowed to say that because I lived there. So I just had them confirmed. Oh, okay, the magnitude of the B field is 1.2 Tesla. Oh, that's nice. It's exactly 45 degrees. So find the magnitude and direction of the force on a 1 meter section of rod. So they're saying that the length then is 1 meter. So using our cross product equation, we've got current, 50 amps. We have length, 1 meter. We have B field, it's 1.2 Tesla. We have an angle, it's 45 degrees. We can plug things in. All right, so that's part A. B, while keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? What is the force magnitude in this case? While keeping the rod horizontal. Are we talking like top-down view? Like if this was lying on the ground? I think so.
I think
All right, because my picture, I think that's why I was confused, because my picture's on the board.
what I think they're saying is like you just keep it on the same plane.
Yeah, so the board you imagine is the floor. That's what they're calling horizontal. This is sitting on the floor. So I can turn it, but as long as it stays on the flat of the board, it's good.
They don't pull it up or something.
Yeah, I couldn't lift it up. Yeah. So how should I turn this to increase the force? Looking at that equation, what angle is going to give that force a bigger number?
45 degrees down.
45 degrees down. So then our final angle would be what? Okay. South of east. So now angle equals 90 degrees. And so before, sine of 45 is something less than 1. I should know that one. Is that 2 root 2 or 2 over root 2? Square root 2 over 2. So what's that, like 0.7? Okay, something like that, 0.7. And then we know sine 90 is equal to 1. So all these numbers times 0.7 is obviously going to be less than all those numbers times 1.
So you're gonna move it so it's in line with the east? Is that what you're saying, move it down?
It's currently in line with the east, but if we rotate it down by 45 degrees,
Oh, it makes it perpendicular.
yeah, then it would be actually pointing southeast.
So what if you went the other direction of 45 and do the same thing, right?
If you put it the other direction, 45,
It'd be 90.
then your angle between the B field and your current in here would be 0, since
So
the
I have
current's
to go,
this direction and B field this direction.
They actually have to go 90 the other direction.
Oh, if you wanted to go like that? Oh, okay, so you could rotate it, what would that be, 90 plus 45, 135. Yeah, you could do that, and you'd have, you'd also maximize the force.
So we just want to get it to perpendicular to the fourth line.
Yeah, anything that's perpendicular to the B field will maximize that force.
And so once you maximize the force, that is the maximum amount of current that will go through?
No, the current you're driving, but that would be how much force that wire feels. So I guess you could imagine that this rod could say roll because it's experiencing a force. So it would roll further because the force is greater if it's at a 90-degree angle. If it's at a 0-degree angle, it wouldn't move at all. And in here, it would like sort of roll, but not as much as if you had it at a 90-degree angle.
Sort of like, I mean, ish, but it's sort of like wind blowing on the rod. Like if if it's in the same direction as the wind, it's not really going to do anything to it. But the closer and closer you get it to perpendicular, then it's going to start rolling faster and faster.
Yeah, that's a really good way of looking at it. Like this B field is sort of like a wind, and it doesn't see the full cross section when it's tilted at this angle. But if you tilt it at 90 degrees, it's seeing the full cross section, and so it's going to get more of a force on the full rod itself. Yeah, that is a great way of thinking about it. So, okay, so that's that problem. So now we're going to make this more engineering-y, less like contrived physics-y problems and more like real engineering problems. So we're going to create a loop of current-carrying wire between two magnets. So how we create that loop of wire, here's a little example of a loop of current-carrying wire. For the sake of the math here, let's imagine that this was squished into a rectangular shape, so that this length is B, and this length is A. And so this is one long piece of wire that's just been wrapped up into a coil. And so if the so in the loop itself, we've got current, and the current would be coming in from one side and then leaving out another side. So we're supplying current in this scenario, and we put that current carrying wire in a magnetic field. So we take two bar magnets and put it on either side, or you actually don't need two, you can just have one magnet because it's creating a B field. So in this case, if you orient the wire like this, like the picture, and the B field is going into the board, so you've got a magnet on this side where the B field is going straight through the center of the loop. Then what's going to happen is it's going to cause this loop to rotate. So you've got current in a B field that's going to exert force on the current carrying wire, and it's going to cause it to rotate. So here's another view of our loop relative to that B field. When it's in this orientation, so the magnet is on the side of it making a B field across the top, then there's going to be a force on either side of that loop, one up and one down. That's going to cause this loop to rotate. And then here's another view, a side view of that wire, if it's rotated a little bit in the B field. So in this view, it's a little bit easier to see the right-hand rule. So if the current was flowing on this front wire here, flowing down, then my right-hand rule, that's my index finger is current. The B field is that direction, like that. Current, B field. What am I doing? Oh, okay. I'm thinking about the wrong part of the wire. Yeah, in the front part of the wire, that's what we're seeing right here is the current going this way. But the part of the loop that's actually experiencing force is the side of the loop that's hidden from view. It's because it's on end here. So the current would be, if it's going down here, it's coming out, and then down, and then in. So it's coming out, down, and then in. So if its current's coming out, the B field's that direction. Still getting the wrong answer. Oh, current. There we go. Current is coming out of the board at this point. The B field is to the left, and then the force is up. Okay, that matches that side. And then the current will go into the loop on this side, so the current's going in, the B field is to the right, I said left, to the right, and then my force is down on this side. And so because this side is being forced up and that side is being forced down, that's what's causing it to rotate around.
Now, is the coil rotating, or the B field is, you're putting the B field as a magnet going in the center of it?
Yeah, so let's assume in this instance that our magnet is fixed. It doesn't move. And our loop of wire is on a little stand so that it can rotate. So it experiences the force. Of course, you can always flip this and have the magnet be the one that rotates and have this be fixed. So that's harder because then you need variable current through your wire. But this one you can use a fixed current and a fixed magnet and it'll cause this loop to rotate. Okay, so I know this is very confusing. That's why we have multiple points of view, but we're going to do the right-hand rule again just so we're clear. So every section of this wire is going to feel a force. On this one, let's do it again. So on these sides, the current is flowing up, the B field is into the board, and the force is to the left. Because that force acts along the axis of rotation, that's not going to help it rotate. So on the same thing is true on the other side, that force is to the right. F4 and F2 aren't actually helping rotation. They're equal and opposite, but they're not going to do anything for us. Up here at the top, the current is to the right, the B field's into the boards, the force is up. And then at the bottom, the opposite is true, the force is down. And you can see if you're looking at it from this perspective, if one is up and one is down, that's what's causing this loop to rotate. So that's qualitatively what's happening. Now the physics behind it requires us to introduce a topic, and I don't think we got to it last term. Did we get to torque? Okay. So I got to teach you torque first. So, this is background information. This is true for any force on an object that can rotate. A rotating force, basically, that's what torque is. It's a rotating force. So we really understand torque intuitively, whether you realize it or not. If you're trying to turn a sticky bolt with a wrench, you automatically grab that wrench at a 90-degree angle and you grab it towards the end because we've learned from experience that it's easier to turn the bolt if you're further from the axis of rotation. And it's easier to turn that bolt if your hand is at a 90-degree angle relative to the moment arm. That's what we call the wrench part, the handle. Sometimes when you're working on your car, you're trying to turn that filter and it's wedged in there behind some engine parts and it's really hard to get to, and you can't get your tool at a 90-degree angle relative to where you're trying to turn it. Sometimes the best you can do is you can push straight up and you're trying to turn the wrench from this point of view. And it's going to be a lot harder to turn it if your angle is this. I mean, sometimes that's just what you have because of the angle of things, but basically you're wasting a lot of your force on the upward motion that's not contributing. The only part of your force that's actually contributing to the rotation is the component of your force that's perpendicular to the moment arm. And I think this is something we just intuitively understand from, playing around with tools in our house. Okay, so the definition of torque in terms of physics is R cross F. R is the distance from your axis of rotation and something we call the moment arm. We call that a moment arm. So it's a distance, so its units are meters. And it's a vector because we're looking at how that vector R compares to the force being applied in terms of an angle. So if you're applying that force straight up here, then the angle between the R vector and your force is measured right here, theta. And so we get the same cross product that we've been doing all day today to calculate torque. And if you just look at this F sine theta part, basically that is just defining, that's the vector component of F that is perpendicular. That's in this case, the radial, what's the F sub t? I just lost it. Radial. F sub r is radial, F sub t is tangent transverse. Tangent sounds good. It's basically tangent. It would. That works for me. Yeah. So, but that's what that would. It would be the component of the force that's perpendicular to the moment arm. So, all right. So, the sine theta, just like we've been seeing with this equation over here, If it's sine of 90, sine of 90 equals 1, so your torque would be biggest if your angle is 90 degrees. Sine of 0, if you try and push on your wrench or pull on that wrench, it's not rotating. So sine of 0 gives you no torque, no rotation. Another weird thing about torque, and I don't know that this really is relevant today, but it comes up later in 223. Torque is positive for counterclockwise rotations and negative for clockwise rotations. And that's just one of those weird rules that you got to write down because there's no rhyme or reason.
Almost like as if you're always measuring degrees from the positive x-axis, then it would make
Yeah.
sense that would increase.
Yes.
Or negative, you go that way.
Yes, and that's really where it comes from, is we always measure positive x going from the positive x-axis counterclockwise. All right, so here's another view of our rotating moment arm. Okay, so here we see again the 4 forces that act on all sides of this current loop. And according to, there's one more thing about torque that's critical. So we also said that we intuitively know to put our hand as far away from the axis of rotation as possible. So your R value gets bigger, that's going to increase your torque. If you tried to push on your wrench down here, it doesn't move. So that's basically setting R to 0. Okay, so that's another thing, is you want this to be 90 degrees and you want R to not be 0. So in terms of these 4 forces we talked about before, the reason that these forces along the sides don't contribute is because they're right on the axis of rotation. So the distance from the axis of rotation, R, would be 0. So the moment arm for these 2 forces is 0, so they don't create any torque. These guys are as far from the axis of rotation as you can get. And we said this whole length was equal to B. Okay, so the radius, the R value, would be B over 2 for this force and that force. And so you'd have non-zero torques, which is what causes that loop to rotate. So I'm developing all of our equations here. As I said, I think F2 and F4, we can calculate those forces. Those are the ones on the sides that don't actually contribute to torque. So their current through every part of the wire is I. The length of the wire along this side is equal to B. So this is coming from our new force equation. So that's the length B. And then the B field is big B. And then sine of 90 would be the angle between the current and the B field. And in this case, depending on how you orient it at any given point in time, the angle might change, but you can find an orientation where the current and the B field would be exactly 90 degrees apart. So if this is your orientation, you've got your B field going that way, and we're talking about the forces on this sides of the wire. So the current would be going straight up on this side and straight down on that side, which would be a 90 degrees angle relative to the B field. So that gets rid of the sine term. So our forces here and here are I little b big B. And then these forces, F1 and F3, are the same, except the only difference is the length on this side was A instead of B. So we have IAB. And then the sum of the torques, we talked about how torques 2 and 4 would be 0 because the R values are 0. And these torques would be non-zero. So that's, torques 2 and 4 is 0. So torques 1 and 3, the R value is B over 2. The force we calculated for force 1 and 3 was A big B. And then theta is going to change as the loop rotates. So we're going to keep it theta in the equation. The negative comes in because of the way I drew my picture. It's going clockwise when it's rotating. So that's why we have to have a negative on our torque value. Yeah, Chris?
So if we start with the loop oriented parallel to the B field, then we won't get any motion.
Parallel to the B field. Let's see.
I guess I'm just trying to visualize
Yes.
like what happens when it.
Oh,
Because if
parallel.
it's always going in the same direction and B is fixed, then when the coil flips over,
Here, let me put this down. So the B field is pointing straight up right now.
right?
Parallel to like this, right? So the B field's up and this is the plane of the coil. Yeah, yeah. So your forces, one force would be pointing straight into the middle and the other force would be pointing straight down. And so, but there's no angle that gets those forces away from, like off center, so you'd have to
Right.
give it a little kick to the side.
But what happens when it flips over if the current is still going in the same direction? I mean, in other words, is it
Yeah.
going to want to do this
Yes.
and then actually make a full
Yes,
rotation?
exactly. So it would do this if you did nothing to the current, you just drove in direct constant current, then your loop would just flip back and forth, back and forth, back and
And
forth.
that's where Tesla started with the AC so that it would flip all the way over.
Yeah, yeah, AC is an option, and there's another option we'll talk about called the commutator. Yeah, that'll cause the current every 180 degrees to switch the direction. So if the forces on the bottom are pointing up because the current is going this way, so the force would be pointing up and pointing down, that's going to cause the loop to rotate. And if you switch the current now to be like this, now the force that was pointing up now points down on this side, and you have to, momentum will carry it over that hump where it wouldn't actually be able to start if it was stopped there. Momentum carries it past that hump and the current switches direction. Now the force is down, and that carries it down to the bottom again. Yeah, so I'll talk about how the commutator is able to switch direct current every 180 degrees. So the current flows one way and then flows the other. So all of this development is just developing a single equation. So we don't really care about the fine details because you won't have to rederive that at home. Yeah, that's right. So I'm going to rewrite it because that yellow box is kind of hard to read. So the take-home equation is that torque net on that loop would be I little a little b times the B field, and then sine theta, the angle is changing as it rotates. And this is, for that square loop, that was equal to the area. So you can write that as I, big A, big B, sine theta. Now, if you have multiple loops of wire, like the one I have as an example, then the torque just multiplies. So you'd have I, and I like to write NBA because that's easy to remember. And any equation that I can remember in my head is always nice. So I NBA sine theta.
Does that area of room for A dot B, A times B, little a times little b, is that applicable to a circular coil as well?
For a circle?
Would you use the area of a circle?
Yeah.
Okay.
Yeah, you just
So
throw
it's-
in pi r squared.
Because of the way the vectors kind of cancel out with each other, it still cancels, it's just not quite as clean and pretty because you got to feel high.
Yeah, it's easier to explain it with a square loop, but in practice you can just throw in the area of a circle.
Could it, in theory, be any shape? I mean, not any shape that's at least symmetrical then?
Yeah, I mean, you guys will, this is exactly what experiment 2 is. You're going to build this little motor. So if you had time, you could play around with different shapes and see if that helps or hinders how quickly it rotates. I think without going through and figuring out the torques and stuff, it'd be hard for me to say, but my guess is that a non-symmetrical loop might not rotate very well. Yeah.
So if you made it like a star shape,
You could, that would be kind of tricky, but you could try and see what it does.
no, that's like the diamonds, like 4-pointed star.
A 4-pointed star, yeah. I mean, it's,
Because it'd be symmetrical.
it would. You just have to, well, that might not be too bad, because with the square, like the sides that are these sides, right? they had a force that wasn't contributing to torque. But if you angled those sides in, then there's going to be some difference now, and you'd actually get some torque on that side too. But I think ultimately the circle is the answer, because then you only have one small point on the sides where it's actually perpendicular, and then it starts curving in right away, and so you're